while again, please let me know. Because all I want to do is now, I want to show you a few materials through the prism or through the lens of this new method, or the method I'm using, called dynamical mean field theory. But actually, what is, or what do I call orbital selective states, is the fact that if you think about an atom and you take the D shell. Now the D shell has 5 orbitals, and this can be occupied with various electrons. Now what's happening is some of these orbitals, let's say you have an atom, like you see here, you put this atom inside of an octahedral environment, and the question is, what's happening with these orbitals? What's their character? Of course, these orbitals can be localized, they can talk to each other and create a band. But the question is, what's the character? And in some cases, it's happening that part of the electrons behave or have a metallic character, and part of them have insulating character. Now, if on one given atom, you have orbitals with different characters, metallic or insulating, we call this orbital selective state. Now, everything started, so I want to mention to you that before doing these numerical calculations or becoming a numerical theorist, I did my PhD in experimental physics, I had a postdoc in experimental physics, and everything started with a particular material. And I had certain questions during my PhD. This was like, more than 10 years ago, but based on those questions, I ended up doing what I'm doing today. And now, before going to theory, I want to explain a bit what do we mean by charge order in some materials. These were questions that I had during my PhD. Now, why do I go and talk about charge order? Phenomenologically, when we talk about charge order in an insulating material, we can think that one ion has one oxidation state, let's say 3+, and other one has 2+. Now, there is a difference of oxidation state, meaning you have difference of charge between the atoms. Now, one way to measure this charge order, it's called resonant X-ray scattering. So what we do in this, usually when you have scattering or diffraction, you send a beam with a given wavelength into your material and you measure the output. This is called diffraction, and it's governed by Bragg law. But in some cases, you don't see any reflection, you don't see any intensity for a given setting, you don't see any intensity for a given wavelength of the incident beam. But then if you change the wavelength or the energy, what's happening is some reflection which are usually absent, they show up. So here I'm showing you for neodymium nickel oxygen 3, 2 different reflections, reflection called 105 and 015. And what's happening is, as I send my beam towards the crystal and measure the output, as you see it here, if I change the energy of this incident beam, by changing the energy, meaning I'm changing the wavelength of my photons, what's happening, I see this change of intensity. With field circles, I see 015, with open 105. And this signal here, it's called resonant X-ray scattering signal. Based on this signal, I can extract some parameters called form factors, labeled F prime, F double prime, and these form factors are basically the scattering power of that particular atom. If there is a difference between 2 atoms, like you see here, so here in this particular neodymium nickel oxygen 3, I have 2 non-equivalent ions. I have something which I call nickel 1 and nickel 2. I'm measuring the form factor, or I'm doing this measurement. I'm extracting the form factor F prime and F double prime for these 2 ions, and I see there is a difference. If I have this difference, any experimentalist will tell you this is proof of charge order. So basically, by doing this measurement, we claim experimentally that we have charge order in neodymium nickel oxygen 3. Now, this is experimental results, experimental interpretation, or phenomenological interpretation. Later on, I will show you that using theory, what we have in this material we have some orbital selectivity, and I'll go further to that. Now, as I mentioned, everything started during my PhD, and what actually started during my PhD? there was this measurement for rare earth nickelates oxygen 3, so neodymium nickel. This was measured. And then what you actually have in this class of materials, rare earth nickel oxygen 3, if you go at very high temperature, you only have one single environment for nickel. So you have one non-equivalent ion. If you lower the temperature, depending on who is the rare earth, lutetium, yttrium, europium, samarium, you go from a metallic state at high temperature to an insulating state in this temperature range. You lower even farther the temperature, you end up with an insulating state where the magnetic moments are orderly. But the particular thing about the metal to insulator transition is the fact that your environment, once you go from metallic to insulating, one octahedra expands and one contracts. Now, in my thesis, I got my hands on this material, silver nickel oxygen 3, where at very high temperature, I have nickel inside an octahedra environment, oxygen octahedra environment, and there is only one side. So I have these layers of octahedra separated by silver, layer of octahedra separated by silver. Now, lowering the temperature, what I see that the octahedra around one side, which I call nickel 1, expands, as you see here. And all the nickel around, which I call nickel 2 and 3, the environment contracts. So basically, I see in silver nickel oxide the same behavior as I see in this class of materials. High temperature, one single octahedra, lowering the temperature, the octahedra differentiate. Some gets expanded, some gets contracted. Now, of course, by looking analogy, I have the same ion, I have the same type of layers. I said, well, I have charge order in silver nickel oxide. I went to the experiment. I did experiments, again, resonant X-ray scattering experiment. Here you have the signal for some Bragg reflections. Again, what I'm doing, I'm measuring the intensity versus energy. In principle, as you see for this 109, away for some particular energies, I should have no intensity, should be 0. But if I go in some energy range, I have this non-zero signal. Using this non-zero signal, I can extract F prime and F double prime for the 2 or the 3 sites, nickel 1, nickel 2, and nickel 3. And I repeat, this, or I'm saying these sites, I know from the crystal structure they are there. I know that nickel 1 is expanded, nickel 2 and nickel 3 is contracted. Now, I'm extracting my form factors. And as I mentioned earlier, these form factors, the fact that they are different between nickel 1 and nickel 2 and nickel 3, they tell me that I have a charge disproportionation. This was all good, and these results went in PRL, and I was the first one to show that I have charge order in silver nickel oxygen 2. Doing some Dft calculation, because of course, as an experimentalist, I was very curious, okay, what does the theory tell me? By doing Dft calculations, I did not get any charge disproportionation between nickel 1 and nickel 2 and 3. Doing all kind of calculations at that particular time as a student, I could not find any difference of charge. And I had the second problem. Besides the fact that Dft did not give me charge disproportionation, the second problem I had was that in rare earth nickelates, I'm going from if I look at the resistivity, I go from a metal to an insulator. If I look at nickel oxide or silver nickel oxide, this system is metallic down to very low temperature. So how is it possible that resonant X-ray scattering tells me that I have charge order in this material, but in reality the material is metallic? This was a bit of a contradiction or something which I could not understand. Now, the best I could do during my thesis, at that time, the only method or the best method available was Dft. Doing the calculations did not give me any charge disproportionation, but still, by doing all kind of, let's say, tricks in the calculation, we could come up with an interpretation that, yes, we have some type of charge disproportionation. And I'm not going in detail unless somebody asks me. On this side, these plots here, all I'm showing, if somebody's interested, I can explain how do we use this resonant X-ray scattering to extract the information that you have charge order in the material. And as I said, phenomenologically, many people are using this method to prove that there is charge order in the system, But silver nickel oxide is one of the systems where charge order and metallicity don't go along. And later on, I'll explain you what's happening in this material. Now, other question during my postdoc was, I looked at this material, bismuth, mangan, oxygen 3. The question was, what kind of orbital order exists in this material? Now, because I did my PhD in experimental physics and mostly I concentrated myself on scattering methods and looking at quantum magnets. By using scattering methods, these are methods I explained before. You send neutrons or X-rays into the material, and when they come out, you measure their properties like energy, momentum, and based on that, you can construct either the ground state properties in terms of the crystal structure, phonons, spin excitations, all kind of things. So when I started to work a bit on theory, it was nice because knowing exactly what experimentalists need, I could go and try to compute those things. And besides silver nickel oxide, which stayed with me for almost 10 years until I could explain, other materials which I started to look while I started my job at Rutgers was lanthanum MnO3 and bismuth MnO3. Now let me explain a bit the external result on these two materials. In lanthanum MnO3, what's happening is at room temperature, you have an orthorhombic symmetry. As you increase the temperature, you have a phase transition and you go to another orthorhombic symmetry. If I look again at some quantity called supercell reflection, what I see is that where I go from one orthorhombic to another orthorhombic, the intensity of this parameter, this Bragg reflection, is going to 0. So at exactly 800 Kelvin, I have a transition because one parameter, something in this system, goes to 0. This is how I define a transition. I have an order parameter. Now, in lanthanum MnO3, this change from orthorhombic to orthorhombic was actually attributed to having orbital order. So I'll explain in a second, but the manganese orbitals, they arrange differently between the crystal structure. So some orbitals point this way, some point up, some point, so you have this type, and that type. But this was the story in lanthanum MnO3, was fully explained by numerical calculations, experiments, phenomenological calculations. Now, what puzzled me, or why I started to work on these two classes of materials, was the fact that if I looked at a similar parameter, again, a supercell reflection for bismuth MnO3, what I saw that you actually have not just one transition, you have 3 transitions. So at room temperature, the system has monoclinic symmetry. Then the intensity of this parameter of this reflection goes towards 0. It has a change at around 400 Kelvin, so this is this transition. Then it has another shape, and here at 800 Kelvin goes to 0. So in principle, here what you have monoclinic to orthorhombic transition. And these two parameters, which I call supercell reflection or Bragg reflections, they actually are measurements which follow the change of symmetry. Now, I'm not sure how much you know about crystals, but what's happening is when you take atoms and you put them together, they can arrange themselves in space to occupy the smallest volume. When they have this volume, by looking at the repetition of the atoms in space, we can define certain type of symmetries like orthorhombic, monoclinic, cubic, things like that. Now, when I started to do DFT or DMFT, all these methods, I was very focused on the crystal structure. So I wanted to understand, is there a method to predict this transition orthorhombic to orthorhombic, or is there a method to predict monoclinic to orthorhombic? So that's what I was sort of interested. At the same time, still question. So now what I'm doing, I'm just showing you how I started to become a theoretician, I could say. I had all kinds of questions, puzzling questions in various materials. I could not explain them. Unfortunately, there are not too many theoreticians, or let's put, there are theoreticians, but there are more experimentalists than theoreticians. And if you go to a theoretician to ask, can you help me with my data? Usually you have to wait a very long time that's the reason why, based on all these questions, I went and started to learn myself theory. Now, another material, and I'm telling you all these materials, as rare earth nickelate, silver nickel oxide, lanthanum MnO3, bismuth MnO3. I'm going now to this class of material because all these materials have what I call orbital selectivity. And soon I'll show you results. What do we mean in each of these materials? What is orbital selectivity and how does this orbital selectivity affect the properties? So another material which I started to work at Rutgers was iron 2 molybdenum 3 oxygen 8. So here what I have basically for the iron ions, I have an octahedra environment, I have a tetrahedra environment. And what was interesting about this material was that by changing the temperature, lowering the temperature, you start to develop electric polarization, which was very large. It's like 0.3 microcoulomb per centimeter square. This is one of the largest values. What was also interesting in this material that by applying a magnetic field, we can change the polarization. So in principle, this material is something like multiferroic, I could say. Now, there are all kinds of details here on this side, where if somebody has question, I explain. But in this material, the interest was that you have an electric polarization lowering the temperature, and the fact that you can change this polarization or control it with a magnetic field. Again, now coming to, these were experimental questions. There was results I had I could not explain. And to try to explain, I started first with phenomenological methods, then DFT methods. And in the end, I stopped at what is called embedded dynamical mean field theory. This method was implemented, or is implemented, in the code developed by Christian Howley at Rutgers. This is the method I like, and because I spent like almost 8 years at Rutgers, I enjoyed the method, but there are many other methods which can be used to explain what I'm doing now in this talk. So maybe the message is that everybody can pick their own method to explain things. Here I'm just talking about one of the methods. I used various methods even for DFT or for DMFT, various codes, and usually all of them give the same result. So independently of what method you use, as long as used correctly, you'll get the same results. As I said, the method of choice, my method is based on dynamical mean field theory. And what's special about this method is the fact that you can explain with this method both states which are metallic and states which are insulating, but I repeat, within the same material. Now, if you work with DFT, it's a method which is based on the fact that the electron has to be free in the real space. So the electron can hop from side to side. And then in order to describe this, you are using band picture, and this is implemented in DFT. Now, if electrons are not really free, but they see each other, then you can have extensions of DFT, like DFT plus U or many other methods, where you try to include in the method the fact that your electron, when you have hopping or when it travels to the crystal, it sees the other electrons. So this is basically describing this part of the plot. These are density of states versus energy. In some materials, which are called mode, what's happening is that the electrons sit on a side, and it costs a lot of energy for them to hop from side to side. In this case, you have to treat the method by considering that the electrons are fixed in the real space. So this is called the Haberline method. My method of choice, dynamical mean field theory, as I mentioned, can explain a system where you have metallic orbitals and insulating orbitals. And this is what I call, I repeat, orbital selectivity or site selectivity if I have this behavior on a particular site. Now, how do I know in this method if I have an insulating state or if I don't have an insulating state? I'm looking at the density of states, as you see here. So I have the density of states, I have a gap, and the fact that I have a gap here, now this particular orbital, I say, is an insulating orbital. But this something which I want to explain here is that, for example, you have systems which are like semiconductors, silicium, or other semiconductors where you have a gap, but the electrons are of S and P type, and you don't have correlations. So there, that gap, it's called the band gap. You can still use DFT to explain that material, And the gap there comes because you have a particular number of electrons such that all these bands are occupied, you have a gap, and all these bands are empty. So that's called the band gap. Now, if you have a system where, for example, you have one electron occupying one band, we know based on Pauli principle that you have to have 2 electrons in each state or in each band, that if you only have 1 electron means that you have this kind of density of states. So half of the band is filled, half is empty. And this is, you end up with a metal. Still, for example, if you look at mangan oxide, where manganese has 5 electrons, you expect the system to be metallic in DFT, but in reality, you see that the system is an insulator if you do the measurement. So now the question is what's happening there? And now there, the reason why you have a gap in mangan oxide is the fact that your orbitals open a gap due to correlations. And this is called the mode gap. Now, in this method, the way you recognize the gap is if you have a pole in self-energy. What is self-energy is, if you have, for example, if you think about the system, the fact that the electron moves to the crystal and interacts with the other electrons, you describe this interaction through what is called self-energy. And if you look at the real part and imaginary part of the self-energy, which I'm plotting here for this particular orbital, if I have this pole within the gap, automatically I know that this orbital, or this gap, it's open due to the correlation. So this is called a mode gap. And I can do, if I have a system with many correlated electrons, I can plot the density of states for each of them. For some of them, the density of states will become metallic. For them will be insulating. But if it's insulating, I can have 2 types, band-like and mode-like. If I have a pole within the gap, I call it mode-like. If I don't have a pole, I call it band-like. Do you have any questions so far?
I'm not sure if you got around to it. Someone in the chat asked earlier if you could repeat what the definition of F and F double prime are.
I do not see the chat. So what F prime and F double prime, so what's happening is once you have scattering by any atom, that scattering of the atom has a few contributions. So it's the Thomson scattering, it's a contribution which doesn't depend on energy, and that's actually what we have for each atom. But in addition, you can have some form factors or scattering which depend on energy, and this is F prime and F double prime. So if you look for any atom when you have X-ray, the form factor has 3 contributions. The form factor which is constant is called Thomson scattering, and you have the form factor which depend on energy. Now, this F prime and F double prime, they depend on energy, and what's happening is they only have a value different of 0, so here is 0, when you have a transition from an occupied level, like 1s, to an empty level, like 4p. So F prime and F double prime actually characterize or tells you that you have if F prime and F double prime are different of 0 at some particular energy, means that this energy can have a transition from a core level to an empty state. So these are atomic transitions. That's what they characterize. F prime and F double prime characterize atomic transitions. If your energy, when you do the scattering, is far away from any transition in the atom, F prime and F double prime are 0. But if your energy is close, like in this particular case for nickel, I'm taking electron from 1s to 4p, the transition, what I call K edge, it's actually these values, around 8.35. Any other questions? Okay, so probably I can move further, Paul, if there is no, I don't see the chat. So if there's any question in the chat, please stop me because I don't see the chat.
Yeah, sorry, I had a question, a follow-up clarification to that.
Yes.
So as I understand your answer, you say that F prime and F prime prime are the contributions to the form factor which depend on energy. But
yes,
what's the difference between them? Like, what is F prime and what is F double prime specifically?
Okay, so they are this. Okay, let me see how to explain this. So the form factor is complex, and f prime is the real part, f double prime is the imaginary part. So your form factor in reality, because we only look at the amplitude of the form factor are complex numbers, and they are related to the Kramers-Kronig relations. But in reality, the form factor, the scattering factor of the atom, it's complex, and f prime is the real part, f double prime is the imaginary part of this scattering factor. It's just a real and imaginary part of the scattering factor. That's the difference. But both of them has a certain behavior when the energy, it's actually taking one electron from 1s to 4p, occupied to empty. I don't know if I answered your question, but
yes, that answers the question. How do you measure the real and imaginary parts? Is one like absorption and the other reflection or something?
Well, what's happening is absorption is connected to the f double prime.
Imaginary part, yeah.
Yeah, imaginary. And you have the real, but in reality, you don't measure these things. What you measure the form factor, which is squared. It's just the value, like I have here, 109, 105, 205. Now, based on the crystal structure, I can write the form factor. I can write this quantity. How does it look for 109, 105, 205? I create a system of equations. I'm solving that system of equations, and I can extract this f prime and f double prime. So what I'm measuring is this signal here. And this is actually positive number because its amplitude is f squared, electron squared, that's the units. I'm measuring this and measuring this for different reflections, writing then the system or how the form factor looks based on each atom. From there, I can extract f prime and f double prime. Now, in reality, many quantities are connected to these two, f prime and f double prime. Absorption is connected to f double prime. What the absorption, if you just do transmission through a material, that absorption is connected to this f double prime. But you don't measure f prime and f double prime directly. You have to measure these quantities from here. And from this, you can extract, by solving the system of equations, f prime and f double prime.
So just 205, 105, 109, etc. This is you measuring the form factor for like different incidence angles or something.
Well, what I'm doing is what 109, 105, 205 means. You have to rotate your crystal such that when you have this, so the point is that if I send a wave here and I'm measuring, for example, the distance between these two layers, this will be a particular reflection, 105. If I rotate the crystal, I can measure different planes. So the difference here is that 109, 105, and 205, they are measurements with the sample rotated differently with respect to the incident beam. So the transfer momentum for this is different. 109, 105, and 205. Once I measure this, this f squared will have, it's a system of equation where this one probably will have, don't forget I have nickel 1, nickel 2, and nickel 3, and nickel 2 and nickel 3 are equivalent. So I will have f prime for nickel 1 minus f prime for nickel 2 in this 109. In 105, maybe this will be with sum, f1 plus f1 prime plus f2 prime. In 205, it can be f prime for nickel 1 plus twice f prime from nickel 2, 3. But all I'm doing is I'm putting the sample in a particular geometry, and I'm changing the energy, and I'm measuring what's coming out, is this signal. I'm rotating the crystal for this setting, changing the energy, do the measurement. And of course, here we measure maybe about 60 reflections, but out of these 60 reflections, you can make them in 3 different groups. And these 3 different groups are basically 109, 105, and 205. I mean, if you look at the paper, I have all the equations there and all the details. But maybe the conclusion would be that the scattering factor has a non-energy term, which we call Thomson scattering. And that has to do only with the fact that, the electron absorbs the radiation, vibrates, and sends it farther. But then if your energy can promote an electron from an occupied part to an empty part, you have to have these 2 terms, which is real and imaginary part of your scattering. Hopefully I was clear enough. If not, But if you
Yep,
want
that
after
makes sense.
yeah, send me an email and we can discuss a bit more about this.
No, that's very clear.
Now, coming back to this method of choice, while I was at Rutgers with Christian Hall, we developed various tutorials to do things on various materials. So at the moment, we can do structural relaxations, we can do phonons, we can compute resonant X-ray scattering, optical conductivity, resistivity, magnetism. So in any material where you have D or F electrons, you expect to have some correlations. And you expect to have these correlations because D and F electrons are a little bit closer in space due to the nature of the orbital. And if they are closer in space, they'll talk to each other, let's say like this. And if they talk to each other, we need to properly take this into account. You can take this into account by many, many methods. One of them is what we call embedded dynamical mean field theory. Another one where maybe you are used with is DFT plus U, and many other methods. If you have any questions about using this code, basically you have here my email address. I'm happy to explain how to use the code, how to go to these tutorials, or how to compute relaxations of the lattice phonons, all these quantities. Last year we developed, for example, phonons in this paper. And why phonons, or why is it important to have phonons in this method, is that in some materials you still have a question when you have a phase transition: who is driving the transition? Is it the electronic properties or is the lattice properties? So it's a phonon-driven phase transition, it's an electronic-driven phase transition, or it's a combination of both. Now, because we have phonons, we can try to explain this question in some materials. And this is an ongoing project with my collaborators. Now let me first, now I'm going to the material I talked before, and I will explain you what the theory gives for all these materials. The first material is neodymium nickel oxygen 3, which I mentioned. And what I told you about this material, I told you that at very, very high temperature, the system is metallic. And this is the electronic property, is metallic. Now, if you look at the crystal structure, what you see is that all the nickel is inside an oxygen octahedra. All the octahedra are the same. So this is at high temperature. Now, we can compute what is called spectral functions, or the properties, electronic properties, where we have energy and momentum. And then we see that where we have the Fermi level, we have bands crossing. So this system is metallic. Our prediction, the spectral function, is in agreement with resistivity, which is a measurement that here at high temperature, the system is metallic. Now, if you lower the temperature for neodymium, what you see is that around 200 Kelvin, this material becomes antiferromagnetic and insulated. Compared to, for example, yttrium, in yttrium, first you have metallic state, you go into an insulating state, where in this insulating state, the spins are still not ordered, and then you go at even lower temperature and you see that the system order. You go to an antiferromagnetic state, and antiferromagnetic state means that the spins are pointing up, the neighboring spins are pointing opposite to each other. Now, looking at the crystal structure in this insulating state or antiferromagnetic state, what we see is that one side is expanded and one is contracted. So now we have two non-equivalent nickel sides, what we call nickel 1 and nickel 2. Now, if we do the calculations with our method for this low temperature state here, what we see now that we have states below the Fermi level, which here is labeled 0, the same there. We have a gap and we have empty states. So basically, our method can describe that you have in the insulating antiferromagnetic state, you have a gap. So first, theory explains high temperature state and low temperature state. Also, one important fact which I forgot to mention is that this embedded dynamical mean field theory method can do temperature dependent calculations. DFT or many other methods are a 0 Kelvin. DMFT, actually, it's a finite temperature method. So for example, if let's go back to mangan oxide, if you look at the magnetic susceptibility, you see that at high temperature you have a local moment which fluctuates. So it's pointing in all directions very, very, very fast, such that in average there is 0 order moment. But you have a moment, you have like an arrow changing all the time there. DMFT can actually is the only method which can properly describe this moving arrow. if you go to DFT, what we call non-magnetic DFT calculations, what you have there is that on site you have zero magnetic moment. So there is no arrow fluctuating, the arrow doesn't exist. So DMFT is the only method which can explain this paramagnetic state with a fluctuating moment at finite temperature. So the fact that now we do temperature dependence, these calculations was done at 200 Kelvin. And then here we do at 100 Kelvin. These are temperature dependent. And you can see that as you lower the temperature and change the structure, you can get the gap. Now, the true reason why we started to study this material was to understand the charge order in this material, and also to understand if, for example, can you get, or is it the anti-ferromagnetic state important for these rares, neodymium, praseodymium, or is not important? And why do I ask this question is because all these lutetium, yttrium, europium, samarium, you go from a metallic to insulating state without having ordering. And then once you go at low temperature, you see that you have antiferromagnetism. Once you move on this other side, neodymium, praseodymium, you go from the metallic state directly to an antiferromagnetic insulator. Now we explain these things, and I'm not going into details. If somebody wants, I can explain. But one outcome of trying to do this calculation was the fact that once we compute the magnetic moment going from the metallic state to the insulating state, we realize that one side, which is expanded, the nickel one, has a magnetic moment, is the blue curve, and the side which is contracted has zero magnetic moment. Now, what I call here distortion is going from the metallic to insulating, so going from this state where all nickel are the same, all the environments, to one environment which is expanded and one which is contracted. But our puzzling was that one side has magnetic moment, one doesn't have magnetic moment. Now, this was a bit interesting, and we said, okay, maybe there is something wrong now in our calculation, because this result was unexpected. So we, based on our calculation, we predict a magnetic state where the expanded side has a magnetic moment, as you see here, but the contracted side, which are this gray arrow, have no magnetic moment. And we said, okay, if this is what the calculation gives, for the moment we leave it like this. But having the question in my mind that this system has charge order, what we did, we started to look at the difference of charge between the two nickels. Now, nickel here is inside an octahedra. If you think about the 5D orbitals, the z square, the x square minus y square, xy, yz, and zy, this we can split in what we call EG orbital. So x squared, z squared, and x squared minus y squared are EG, and the other three are T2G. Since nickel here is D8, means that EG is completely filled. And then let's look at the, sorry, T2G is filled. Let's look at EG. So what we do, what I'm plotting here, if I go in the metallic state, both nickels have, for example, 197. This is the charge in my EG orbital. If I look at the charge in the total 3D shell, it's something like 7.87. Now, by going from the metallic to insulating, where I distort, one side becomes expanded, one contracted, I see tiny difference of charge. And this tiny difference of charge is from 197 to 190, or if I look at the whole shell, from 177.87 to something like 7.82. Of course, now we can play at the question is at which charge do you look? Charge in this orbital, charge in all the orbitals. But if we look at the charge on the whole atom for the expanded and contracted side, because that's what I have, this is the main result, or the final result is this red curve. And what we see is that basically, once I go from the metallic state to insulating state, this difference of charge is within the error bar of the method. So experimentally, our method gives us no charge disproportionation in neodymium nickel oxygen 3. Although, if you remember at the beginning, I showed you these experimental results of resonant X-ray scattering, where we had charge disproportionation. So now we had two problems. One problem was that in reality, we get, from the magnetic point of view, we get one side which is magnetic, one is non-magnetic, although experiment says both of them should be magnetic. And then we get that there is no charge disproportionation. So we said, okay, our method is quite wrong, or the method maybe is not good to explain this material. But still, the material is correlated, and it has all the ingredients for this method to work. And then we said, okay, what do we know? We know, if you remember from the beginning, that there were some measurements of this resonant X-ray scattering signal as a function of energy. And here you see this circle. So the circles are the experiment. This is the true measurement. This is the intensity. And then we said this is for 105, this is for 101. If I go quickly, this is what I showed you at the beginning. So you see this is the measurement. Now from this measurement, I'm extracting this real and imaginary part of the form factor, and this, from the experimental point of view, tells me you have charge order. Our DMFT method says there is no charge order in the system, but then we said, okay, let's take our calculation and try to see if we can reproduce the experimental data for these quantities 105 and 101. Here there are some details of the calculation. Now here we're computing the real and imaginary part of the form factors for the expanded and contracted, and to our surprise, once we took these form factors and computed what we call the experiment, you see the blue curve is basically our calculation. So our calculation, the blue curve, can explain the data for 105, and it can explain at least the main features for 101. We have a bit of a problem here, but this can be also scaling or other things to experiment. But you have a peak here in the data and experiment, peak here, peak there, peak here, peak, peak, peak. So basically, what we show now is that without having charge order in the system, we can explain the experimental data of resonant X-ray scattering. So now we come back to what actually happens. We have no charge order, and we can explain external data. So what is said? I'm asking what is happening, and then we started to look now at the two sides. So what's happening is the following: is at high temperature, all the nickel sits inside an octahedra, and all the octahedra are equivalent. Nickel has 8 electrons, and because of the environment, the energy level are split into 2, 1, and 2. If you start now to populate these levels with electrons, you get 2 electrons, 2, 2, these are 6, and you end up with 2 electrons in what we call EG orbital. And this orbital here is metallic at high temperature. Now, once you lower the temperature, what we see is one side expands, what we call nickel 1, and one side contracts, which we call nickel 2. Looking at the electronic properties in our method for nickel 1, the T2G shell is completely filled, we call it band-like. But if you look at EG, in EG, these 2 electrons, before were metallic, for nickel 1, they develop a gap. We look at the signature of the self-energy, and we say, okay, this is a mode gap. We go now and look at the same properties for nickel 2, for the contracted side, and what we see that, again, T2G is completely filled, but EG has a gap, but there is no Pauling self-energy. This means that this gap is created due to the covalent effects with oxygen, and in this case, you end up with what is called a band gap. So what we discover is that by looking at the properties within our method, even though at high temperature all these sides were equivalent, at low temperature one side is mode and one is band. So in here, the orbital sort of selected what they want to be, in which state they want to be, and one of them wants to be in a mode state, and one wants to be in a band state. So, and now the fact that this state where you have mode and band combined in the same material can explain the resonant X-ray scattering, we came up with a different interpretation. What's happening is that in materials where you say that you have charge order based on the resonant X-ray scattering method, like here, in reality, you don't have a difference of charge in real space. What you have you have a difference of the energy dependent of the charge. And what I mean by energy dependent of the charge is that some orbitals can have a mode character and some orbitals can have a band character. Now, even further, since we see that for the contracted site, the orbitals, they all have a band-like character. What does it mean, band-like character? It means that the band is completely filled by 2 electrons. Now, if a band has 2 electrons, one spin up, one spin down, means that this band cannot have a magnetic moment. Now, by looking at the electronic properties, we understood why one side has a magnetic moment and one doesn't have a magnetic moment in our calculation, which before we thought it's a little bit puzzling. So the side which is mode has a finite magnetic moment, which is spin 1 because I have 2 electrons. The side which is contracted, it has 0 magnetic moment. And like this, we show that in rare earth nickelates, in neodymium nickel oxygen 3, what we call charge order is not charge order, but it's a fancy state where one side is mode and one is band. In a current project, I did calculation for the whole series, not just for neodymium, lutetium, yttrium, europium, all this, and I'm finding the same effect in all the materials. So now we can generalize that what is called charge order in neodymium nickel oxygen 3, in reality is just that the ions want to behave differently within the same material. Now, I said to you at the beginning that experimentally people said there is charge order in rare earth nickelates. And since the system was insulating, yes, you can say that you have a difference of charge between the sides, expanded and contracted. But silver nickel oxide, the problem was that the system is metallic, cannot really have a charge if you think like different charge in space. By doing calculation on silver nickel oxide, what we see is that the side which expands, it's correlated and develops a magnetic moment, and the side which contracts, it doesn't have a magnetic moment and is metallic. So in reality, I don't really have charge order in silver nickel oxide, but I have 2 sides which, again, one is more correlated than the other. The one which is correlated has a local moment. The one which is not correlated has zero local moment. So with these results, basically what I'm concluding is that when people say that you have charge order based on experiments like resonant X-ray scattering, you have to look a little bit carefully because you don't really have charge order, but each site can behave differently. And I'll show it to you at the end of this talk that I went in other materials where people claim that you have charge order, and what I showed that in those materials where people claim you have charge order, in reality, different ions have different electronic properties. Do you have any questions so far? Okay, so let me now clarify the last point before I'm moving further. So what I said is that our theory tells us that one side has a finite magnetic moment, as you see these sides here with blue and green, and one side has 0 magnetic moment. So this is what theory proposes. In experiment, people proposed that the magnetic state the magnetic structure is such that each side has a magnetic moment. So you have a magnetic moment here, which in my state is not there. Looking at the external paper, what we realize is that to fit the external data for praseodymium and neodymium, there were 2 possible models. One model where both sides have a finite magnetic moment and equal, and one model where one magnetic moment was large and the other one was 0. So actually, the model we propose, it's consistent with the external data. The experimentalists, when they fitted the data, they saw that, but at that particular time, they had no reason to think that one side should have 0 magnetic moment. So basically, what we did with theory, we came and we showed that some of the results needs to be reinterpreted, or you need to think a bit more about it. Now, if we found that in neodymium, you have one side has 0 magnetic moment, this means that this magnetic state is not correct. The same would happen for holmium, samarium, europium, and yttrium, where people, again, when they did the fits of the data, they got a solution where both sides have a different magnetic moment. Sorry, have a magnetic moment different of 0. Now, what I'm showing here, this is a magnetic state obtained from X-ray. And as you see, this magnetic state obtained from X-ray is very different from the magnetic state obtained from neutrons. And again, the reason for all these discrepancies is because people try to fit the external data by considering that both sides have a magnetic moment different of 0. But we also took, if you look at our paper, we took this magnetic state, and with this magnetic state, we could fit both the neutron data and the X-ray data. So we believe that this is the true magnetic state for neodymium nickel oxygen 3, not the one where you have finite moments on both sides. So if I'm talking too fast, or I don't know, maybe it's too much information, but don't forget, all I want to do now is I want to show you examples where the method worked to give us more insights into experiments. There is a lot of information here. As I understood, you are all students, so probably a lot of new information, but I'm just giving you, this is what the method can do in all these materials. If you have questions, I'm happy to teach you or discuss with you or show you how to use the code. Anytime you want, just send me an email and we can discuss about any detail you want, or if you have your own compound, at least I can suggest what experiments you can do or what calculations. Now, I finished with neodymium nickel oxygen 3, and the main message you should take here, or what you should take home, is that what people believed before, that is charge order in this material, and charge order or disproportionation in the sense that you have different of charge for nickel on real space, we show that actually this charge disproportionation in terms of theory can be interpreted as different electronic properties for various sites. In this particular case, the site which is expanded is a mote-like, and the other one which is contracted is a band-like. Now I'm going back to the next class of material, which here I had iron 2, molybdenum 3, oxygen 8. And as I said, this material was interesting due to the fact that it showed a large polarization when you lower the temperature. So that was basically, this was the main interest for us, is why do you have this huge polarization change as you lower the temperature? Now, I worked experimentally on this one on manganese compound and iron compound. I sorted out the crystal structure, and here you see the feeds of the data. Now, the structure, as I said, you have layers of tetrahedra and octahedra, where inside you have the transition metal manganese or iron. Then you have a layer like here where you have molybdenum trimers, and then again you have a layer of transition metal iron. So this is a very complicated structure. Besides having this large polarization, you can also tune the electric polarization with the magnetic field, which makes this material more interesting. Now, what I did for this class of materials, I did calculations for this class where you have manganese, iron, cobalt, nickel, and zinc. And what I'm showing you here is that by looking at the properties of the orbitals in these materials, I discovered a very interesting state, which I'll explain in a second. But let me guide you through a bit. So what you have, this is the crystal structure. I have tetrahedra and octahedra, and inside here I can have manganese in both sides, iron, cobalt, nickel, and zinc. Now, on this side, you have the electronic properties of the tetrahedra. On this side, you have the electronic properties of the octahedra. If you look at how the states, the 5D orbitals split, you see that in the tetrahedra, they split into 2, 1, and 2. For the octahedra, it's 2, 1, and 2. The only difference is that this one is 1. It can be higher in energy or lower in energy. Now, if I go at the manganese, manganese has D5, has 5 electrons. For the tetrahedra, each orbital is occupied by 1 electron. The same happens for the octahedra. Now, if I look at the density of states for what I call here EG, T2G1, T2G2, if I look also at the density of states for the molybdenum, I see that I have a gap. So I have a gap for the tetrahedral side, I have a gap for the octahedral side. This means that my system is gapped. The question is this gap band-like or mote-like? Now, if I go and look for a pole in the self-energy, here I'm plotting self-energy density of states. If I have a pole, automatically I can say that this orbital is a mote. It's mote type. If there is no pole, this is band-like. And what I did for this class of materials, basically, I looked at all these properties, and these are, all kind of plots showing is band-like or mote-like. But what was interesting is for iron, tetrahedral side, I have here a state where these are two divergent orbitals with 3 electrons. Looking at the density of states, I see a very, very strong resonance. It's a peak in the density of states. It's a flat band in the spectral function, but this was quite interesting. And the question was, what is this resonance? I only find it for iron and on the tetrahedral side. And now to understand what is this state, what we did, we went and looked, for example, at the temperature-dependent properties. So I have the tetrahedral side, I have the octahedral side here, and I'm varying the temperature. So what I see is that this resonance from here has a very strange behavior. At low temperature is very sharp, but as I increase the temperature, it is decreasing in intensity. You can see it better here. All these other states for the tetrahedra or the octahedra don't have too much change with temperature. So the first observation is that temperature, increasing the temperature kills this state. Then we also looked how this state behaves as a function of what we call correlations, the Coulomb repulsion, or the correlation called exchange coupling or Hund's coupling. And what we see is that this state has a behavior of a condor-like resonance. Now, in some metals where you have F electrons in heavy fermions, what's happening is that you have this, let's take cerium. Cerium has 1 F electron, and this electron, at high temperature, it doesn't talk to the conduction electron. So you have a material where you have cerium, and then, as I said, you have 1 electron in the F orbital. You are at high temperature, the F electron doesn't talk to the other S and P electrons. The system is metallic, and everybody's happy, I could say. But now once you lower the temperature, the conduction electrons and the F electrons, they start to talk to each other, and towards at very low temperature, this electron or the magnetic component, the spin of this electron gets screened. And that's it's called, in simple words, a condor resonance. Now, what we see in our case, in this material, we see basically that we have a peak, which increasing the temperature is decreasing. And now, if you look at the magnetic susceptibility as a function of temperature, we see that for the tetrahedra, the susceptibility is decreasing as you increase the temperature, as you decrease the temperature compared to the octahedral side. This susceptibility trend combined with the temperature shows that you have something like a condor resonance in an insulator. This is the first observation of a condor-like resonance in an insulating material. You have it a lot in metallic systems, but you don't have it in the insulating materials. Now, the expert evidence of this is basically the gap. Here you have measurements of the gap. Here are the values of the gap for the iron compound, iron zinc, zinc compound. You also have manganese, nickel. Doing the calculations and doing the experiments, we can explain quite well the gap values. What's happening is that if you look at all the gaps, the iron has the lowest gap. Now, why does the iron, if you look now at our properties, why does the iron have the lowest gap? The iron has the lowest gap because you have this resonance here. So in principle, in this material, in this class of material, this condor-like resonance, which is seen for the first time in an insulator, is validated by the optical conductivity. And when I say validating, is that the gap we obtain in the iron compound is the smallest, and it has to do with this resonance which appears here. So it's like basically we can think of this state where I have 1 electron, and this electron is screened somehow by the other electrons, even though the system is insulating. Now, why these materials are called, or where is the orbital selectivity here? The orbital selective in this class of material comes from the fact that I have, in manganese, all the orbitals are mode on the tetrahedral side, mode on the octahedra. I'm going to iron on the tetrahedra. These states are mode. Now this one here, it's band-like with this very interesting resonance. If I go on the octahedral side, I have mode plus band-like with no resonance. In cobalt, I have basically mode and band, and I have mode and band, but this band on the octahedral side is band due to the covalent effects. I go to nickel, I have mode and normal band because of the filling of electrons. So even here in this class of materials, even though they are insulating all the time, it is a different type of insulating. Insulating due to the correlations, insulating due to the band filling, like you have here, for example, insulating due to some interesting state or what we call Kondo resonance, or insulating because you have covalent effects between the nickel and the oxygen in the environment. So this is also some kind of orbital selectivity. Okay, any questions so far? Can you still hear me? At least to check that you are still there. Okay. I said, I'm sorry if this one looks very complicated, but all I'm trying to say with all these things is that now you are probably going in theoretical fields, but it's good to know a bit. So I started experimentalist, and I ended up doing all these calculations with various methods, and I did DFT plus U, various codes, ended up with DDMFT, because I wanted to understand the experiments. Now you are theoreticians, and I want to show you that if you look carefully, there is so much agreement between experiment and theory, and actually theory can guide you to do experiments. I have cases, since I'm back in Romania, I have proposals where I first did the calculations on hypothetical structures, then I went to experimentalists, they prepared the material, we went and measured, and actually we tested the prediction. Of course, I did maybe like 50 predictions or more than 50, and one worked out, but still this is a good success. Now moving next to these two materials, lanthanum MnO3 and bismuth MnO3. The crystal structures for lanthanum, both, so at room temperature, I have orthorhombic symmetry for lanthanum, monoclinic for bismuth. And what's happening is that in lanthanum MnO3, I have one single environment for manganese in lanthanum. In bismuth, I have two. So here, it's manganese is green. Here I have blue and green. So what's happening is, as I said, two non-equivalent sites in bismuth and only one site in lanthanum. Doing resonant X-ray scattering, the method I mentioned to you, apart from the fact that with this method you can measure charge disproportionation from the phenomenological point of view, you can also look at the orientation of the orbitals. So now let me tell you what was accepted in the literature for lanthanum MnO3. If you look at the oxidation state of manganese in lanthanum compound, it's 3+. This means I have 4 electrons in the d orbital. Now what's happening is if you try to take the mangan, put it inside the octahedra, you have the splitting of the 5d orbitals grouped into 3 orbitals, which you call T2G, and these T2G are XY, YZ, ZY. And then you have EG, which is Z squared and X squared minus Y squared. The fact that one electron occupies 2 levels, this means that you have spin entropy. So this electron, the spin can be up and down, but also the electron can hop between one orbital and the other. So basically here you have quite a large entropy. And what the system will do in the end, the system will distort, the lattice will distort such that you split these 2 levels into the Z squared and X squared minus Y squared. So this electron will occupy the lowest orbital. And now, depending how the splitting in the lattice goes, these Z squared orbitals can point in various directions with respect to the lattice parameter ABC. So in lanthanum MnO3 was proved by using resonant X-ray scattering that you have orbital order. And this orbital order happens because you have this distortion of the lattice to lift the orbital degeneracy in the EG orbital. And this is called something like Young-Taylor distortion. Now looking, and this was, clearly observed many experiments, and then I said, okay, how does this orbital order looks into my method? I showed at the beginning of my talk that there are these Bragg scattering, or these scattering quantities, which if I measure, it has finite intensity or finite values up to a certain temperature, here 800 Kelvin, and 0 after that. Now this was interpreted like where the signal is basically finite, means you have orbital order, and once you cross this point and there is 0 intensity, you don't have the orbital order anymore. Now what I did, I went and took crystal structures at room temperature, somewhere around 600 Kelvin and somewhere at 900. I mean, actually it's 300, 600, and 800 Kelvin. And I did calculations. So doing the calculations on lanthanum MnO3, I have only one site which is non-equivalent. And this site you have the EG orbitals and the T2G orbitals. And what I'm seeing is that at room temperature, all the orbitals are insulating. So T2G are insulating, EG are insulating. Now, as I increase the temperature to 600 Kelvin, I see that T2G orbitals are still gapped. EG, I see that the gap is closer. So see, here you have a clear gap. Here, the gap is not, I mean, it's there, but it's smaller. Now, moving at 800 Kelvin, so above this transition, what I see that T2G is basically still gapped, but EG orbitals become metallic. So what was interpreted phenomenologically as orbital order, so I have orbital order here, and then I go to orbital ordering being killed. If I look at the electronic properties, here I have an insulating state, and when the orbital ordering is killed, I have a metallic state. Now, this was sort of expected. I expected to find a metal, because if I kill the orbital order, what does it mean? It means that I'm killing this distortion here. If I kill the distortion, I have 1 electrons in 2 levels. The system has to be metallic. But what I did not expect is the T2G orbitals to still be insulating. So what you see here at high temperature, you see one mangan site where 2 orbitals are metallic and 3 are insulating. These 3 insulating orbitals are moth-like, so the gap is opened by correlation. Don't forget, in each of these orbitals, I have only 1 electron. Now, if you have 1 electron in 1 orbital and no correlation, you expect to have metallic state, because Fermi level has to cut your band into 2. The fact that here I have a gap means that this is moth state. So lanthanum MnO3 at high temperature actually has orbital selectivity. The evidence for this orbital selectivity you can see in the resistivity. If you look at the resistivity, which I don't have in these slides, but if you look at the electrical resistivity at high temperature, you see that the value it's much larger than the value you have for normal metals, and is much larger because you have electrons into EG, which are metallic, but you have a huge scattering because you have a fluctuating moment on site. So when the electrons travel to the crystal, they'll have scattering because of the localized T2G spins. So this is another example of orbital selectivity. And all I did so far is I looked phenomenologically at what people call orbital order at low temperature. And once you go at high temperature, people said you don't have the orbital order. Now, in terms of my method, what I'm showing is that what people call orbital order, in my case, I have all the orbitals are insulating. Some are insulating because of the band-like, some are moth-like. Once I go in the what is called orbitally ordered killed state, some orbitals are metallic, some are still insulating. Now let's go back to bismuth MnO3. Here things are becoming very interesting, because what was proposed, it was proposed that at room temperature, you have orbital order in bismuth MnO3. But as you increase the temperature, you just kill the orbital order, and then once you go above, like, 780 Kelvin, you destroy this orbital order. And my question was, since you have this strange or the different change, you have intensity coming to here, you change the sort of decrease, means that something happens between here and there and this third state. If you look at the resistivity, you see hysteresis at this point and at that point, meaning that these are true phase transitions. So basically, in bismuth MnO3, I have monoclinic at room temperature. I have one state. I have an intermediate state, and then I have a high temperature state. The question was, how do I see this orbital order in bismuth MnO3? So I went again and did the calculations for this material. I went at room temperature. Don't forget now that in bismuth you have two non-equivalent sites for manganese. You have the green and the blue. Here I'm showing the results for one side, the green, here for the blue. So what I see is that at room temperature, all the orbitals for both sides are insulating. Again, what I call T2G, it's moth-like. What I call EG, it's band-like. I'm increasing the temperature to cross in the intermediate phase, or in this phase. Now looking here, what's happening is that in both, I still have two sides, even in here. But if I look in these two sides, the T2G, it's moth for both sides. But one side has metallic state already, one side is still insulating. So basically, what I see here in the intermediate phase is that the orbital order is killed on one side, but is preserved in the second side. If I increase even further the temperature, what I see is that this EG, which was still insulating, becomes metallic. Now, if this one becomes metallic, this atom and that atom are equivalent. So now, if both atoms are equivalent, what I will have one type of atom where EG is metallic and T2G is basically insulating. So by using my method, what I realize is that at room temperature, I have orbital order on both sides. At high temperature, I have orbital selectivity because one side is insulating, some orbitals are insulating, some are metallic. But in between, in this region, I have what I call partial orbital order, because one side still has the gap. So one side still has this type of distortion, still has the Z² orbital aligned, but the other side is metallic. I don't have orbital order. So I call this intermediate state site orbital selective mode. Site because the sites are different, but on each side, some orbitals are doing something like being insulating, some are metallic, some are band-like. So this is another material, bismuth MnO3, where basically I have fancy states. For lanthanum and bismuth, people claim experimentally or phenomenologically that you have orbital order, and by using this DMFT method, I show that this orbital order can also be interpreted in terms of site and orbital selectivity. For the previous compound, neodymium nickel oxygen 3, phenomenologically or experimentally, people said you have charge order, and I showed again you can see this charge order in terms of some orbital or site selectivity. Now I can also look, for example, in this about each time when you have a transition, you have to have some order parameter. And for example, in lanthanum MnO3, I have an insulator below 800 Kelvin or in the orbital state, and then I have a metal at high temperature. So I go from insulator to metal transition. For bismuth, I have insulator to metal transition, so it's like this. And then from this metallic state, I have a different, so metallic state here, metallic state there. But now what's happening is the fact that these sides become metallic, I have a structural transition. So the order parameter here between this monoclinic to orthorhombic is actually structural phase transition. I don't think I have time now to go in these details, but when I look at all these energy-dependent properties like density of states, I can see that I have orbital order, orbital order in the insulating state, and I have no orbital order in the metallic state. Here I have orbital order, partial orbital order, no orbital order. I can also look at the occupation of these orbitals and actually recover this phenomenological picture. That's possible. Now, one interesting thing I mentioned to you at the beginning, once I saw that this method can explain quite a few properties which could not be explained by other methods, or now I'm trying to give a different interpretation. The question was, can I predict some of these crystal structure and some of these states? Now, if I have an octahedra, any distortion away from octahedra, I can characterize by the bond index. I can call bond. So how much the bonds distort, or if I have an ideal octahedra, all these angles are 90 degrees, I can characterize by what I call bond index. But what I did now, I took the lattice parameters of lanthanum MnO3 for the phases insulating metallic, and better metal, and I looked at the experimental properties called bond index distortion D, and these values computed for the experimental structure are these empty symbols. Then I went and did structural relaxations of my structures at various temperatures. And what I saw that I'm actually recovering almost the same parameters. Independently, if I have a band mode or cite an orbital selective mode or orbital selective mode, it seems that my theory can predict these states. So this was quite an interesting result for me, because I'm showing that I have a method where I can predict not just the structure, but I can predict even the electronic properties, or in other words, I can predict electronic structural interplay in correlated materials. So based on these successes so far, I decided that I can use this method as my method of choice, because whatever material I take and do calculations, if it's correlated, I can get these fancy results, which then I can test against experiments. Or if the system is not correlated, I will end up with the DFT results. Now, what I want to mention here is that for bismuth MnO3, none of the other methods could get the gap. I think there are more than 15 different types of calculations to get the optical gap, and DMFT gets it right from the beginning, from the first calculation, with no tuning, with nothing. So the validation of our method was the fact that the optical gap was properly computed by the method. Now, moving further, I have this material calcium iron oxygen 3, which I started to study after I went to a conference, and one experimentalist saw some of the results I showed you, and they said, well, in calcium iron oxygen 3, you have quite strong charge order 4+ and 2+. So how does this charge order looks in terms of your method? And then I went a bit and looked at this. I don't know how much time I still have. Maybe a few minutes. Can you still hear me?
Yes.
Do I still have like 5 minutes, or?
I mean, yeah, in theory, yeah.
Okay, so I will go quickly through. So this last material, the idea was, again, you have charge order. Experimentally, what's happening is you have a metal to insulate a transition without magnetic ordering. Again, at high temperature, you have iron inside of octahedra. All the octahedra are identical. You lower the temperature, you go and you have one octahedra expanded, one octahedra contracted. And you have expanded, contracted in terms of the crystal structure. People have done all kind of Mouse-Bauer spectroscopy, so now it's different than resonant X-ray scattering. And the Mouse-Bauer spectroscopy said that in calcium iron oxygen 3, again, you have charge order of, or oxidation states of 4+ and 2+, meaning you have almost 2 electrons difference between different iron sites. Which, from my point of view, I said this is not really possible based on the experience with other materials. Doing calculations, what I realize is that if I go in the metallic state at high temperature, what I discover is that the 5D orbitals, they split into 1, 2, and 2. And when I say 2 and 2, these two have the same energy, these two have the same energy, and this is just 1. Now, if I look at the occupation, I see that iron is D5, quite unusual for this material. And then each electron occupies one orbital. Now, one of the orbitals is mode, and the others are all metallic. So that's why at high temperature, this is metallic state. Lowering the temperature, what I see is that the expanded octahedra, all the orbitals now are becoming mode. For the contracted, the T2G is mode, e.g. it's band-like. So compared to the other materials where, for example, T2G, like nickel has 8 electrons, so these orbitals were completely filled, and that was a gap, band gap, because of the filling. In this calcium, iron, oxygen 3, I see that I have mode here on the contracted side, and now I have band gap through the hybridization with oxygen. This type of hybridization, which happens also in neodymium nickel oxygen 3, is called negative charge transfer if you look in the literature. But again, I show that in this material, basically what people call charge order, it's again different behavior of the orbitals on site, mode versus band-like, or mode versus metallic. Here I'm just showing the spectral function of the metallic state that I can reproduce in metallic. Here I can reproduce that at low temperature. I have a gap. The gap is quite nice. I mean, it agrees, not quite, it agrees with the experiment. Here I'm showing density of states for these materials, for these orbitals. Now, I don't have time to go into this, but again, here I looked how well my method can predict the electronic structural interplay in these materials, and I can get quite a good agreement. Okay, so I got to the end, and hopefully you are not too confused, not too tired, and not too bored. But what I wanted to show you in this talk is that if you know theory and a bit of experiment, or if you know experiment and a bit of theory, it can help you to actually guide the science in a different way. So in my case, first I start with the experiment. I start with a crystal structure. Now, once I have a crystal structure, I can quickly figure out from the crystal structure, just looking at some, magnetic susceptibility, if do I have some correlations or not. And then using the lattice parameter, I do a relaxation of the structure at high temperature. And then I look if the system is metallic or insulator. I'm looking if I have a local moment. I'm looking for phonon instabilities. Now, if I predict that I have a local moment, the next measurement is magnetic susceptibility. If I predict that I have an insulator, I'm measuring the optical gap. I can also look if there is magnetic ordering, and then I can look in the magnetic susceptibility if I have ordering. Once I validate part of my calculations, like local moment, metal insulator correlations, then I can go and do further theory predictions. I can go and try to see if I lower the temperature, do I end up with the magnetic state? Do I end up with a phase transition, which is electronically driven, not by magnetic ordering? Do I have a phonon instability? So by combining experiment and theory and the prediction power of the theory, I can find novel states of matter. By discovering these novel states of matter, what I can do, I can find novel functionalities, or in some cases, if I understand how a material works and has a particular functionality, I can improve on these functionalities. So it's good from my point of view to go and learn a bit of experiment if you're theoreticians, and then try to see which theoretical methods, or not which, all the theoretical methods actually give you insights into the experiments, and you should combine experiment and theory to get to the bottom of your problems. Thank you very much for your attention, and if you have any questions, I'm happy to answer now or any time after this talk. If you send me an email, we can discuss in private. I can reply by email, but I'm happy to answer any questions related of what I talked here in these slides. Thank you.